about continuity. So you've encountered continuity at various points in mathematics, and at different stages you've probably had different definitions of continuity. Kind of the earliest definition you may have had of continuity is that x is, or a function f, is continuous at a point c if you don't need to lift your pencil when drawing the function around c. So, we're drawing some function f of x, and around the point x equals c, we didn't have to lift our pencil, so it was continuous there. Whereas maybe it continues on and we've got something like this. We've got like a jump discontinuity. So this function would be continuous at c and discontinuous, not continuous at, let's call this k. So that's an informal definition. Another definition you probably saw in calculus was that a function f is continuous at the point x equals c if the limit as x approaches c of f of x is equal to f of c. So again, if we're thinking about that definition, the limit definition, then that's saying as x approaches c from either side, then f of x is approaching f of c. So as x gets close to c, f of x gets arbitrarily close to f of c, and yes, that's happening, great. Whereas over on the other side at k, as x approaches k from either side, we see that there is not one value that is being approached. So here is our f of k up here where the filled in circle is. But for these values that are close to k, for x close to k on the right-hand side, we are not getting close, f of x is not approaching f of k. So again, we're discontinuous at k. And in both these cases, we said that a function f is continuous on an open interval if it's continuous for all elements of that interval, and if it's continuous on the interval from negative infinity to infinity, then f is just simply continuous or continuous everywhere. So with that limit definition above, the question is then, how was limit defined for you? In Calc 1, it's likely that you had a sort of informal definition of limit, which again was that the limit as x approaches c of f of x is equal to some number L if, as x gets close to c, f of x gets arbitrarily close to L. And then we have a really, similar picture here. Maybe let's put L down here. So we would say that the limit as x approaches c of f of x is equal to L if it's the case that as x gets arbitrarily close to c, f of x gets arbitrarily close to L, as is happening here. That is a definition in words. To make that more formal mathematically, here is the epsilon-delta definition of limit. So we'd say that the limit as x approaches c of f of x is equal to L if for any epsilon greater than 0, there is a delta greater than 0, such that for any x not equal to c, the absolute value of x minus c, in other words, the distance between x and c in the real numbers with the usual metric, if that distance is less than delta, then it must be the case that the distance between f of x and L is less than epsilon. So let's write this again and visualize it. For any epsilon greater than 0, there is a delta greater than 0 such that the distance between x and c being less than delta implies that the distance between f of x and f of L is going to be less than epsilon. So it's saying, okay, give me any epsilon you want. Here's a small epsilon. This is L plus epsilon. This is L minus epsilon. And I want f of x to be within that window of, L minus epsilon to L plus epsilon. Now, this is telling me that given that small window I want to get in, there is some delta that I could say, as long as x is within that window, not necessarily actually being equal to c, this x minus delta, x plus delta, as long as I'm in that window and not necessarily equal to that point C, then f of x is going to be within this window, L minus epsilon to L plus epsilon. So visually, that's what's going on. An important thing to note is that if we're just talking about limit overall, then it might be the case that we have a removable discontinuity at C. So it might be the case that f of x is not actually equal to, that f of C is not equal to L if we're just talking about this definition of limit. However, now if we combine that together with our definition of continuity was that the limit as x approaches C of f of x is actually equal to f of C. So this requires that, yes, that this limit exists and is equal to f of C. So this would be f of C, and that is the limit of this function as x approaches C. So in other words, the definition, the epsilon delta definition of continuity of a function is, for any epsilon greater than 0, there is a delta greater than 0, such that the distance between x and C being less than delta requires that the distance between f of x and f of C will be less than epsilon. So this is our epsilon delta definition of continuity, and it's saying as x gets close to C, f of x must get close to f of C. That is our definition of continuity for a function mapping the real numbers to the real numbers. So let's use this definition of continuity to show that the function f of x equals negative 2x plus 5 is continuous. So in other words, we're saying let epsilon be some arbitrary number that is greater than 0. Find me a delta greater than 0 such that x minus c being less than delta implies that f of x minus f of c must be less than epsilon. So pause, try that out. We'll talk about it in a moment. So we want to show that f of x equals negative 2x plus 5 is continuous. We sort of intuitively know that any linear function is continuous, but let's now prove this for this one using the epsilon delta definition of continuity. So we're letting epsilon be a positive number. We want to find some delta greater than 0 such that x minus c being less than delta implies f of x minus f of c is less than epsilon. We're doing this for an arbitrary point C, so that will tell us that this function is continuous everywhere. So let's think about this particular function. Let's look at, what is f of x minus f of c. So let's just plug that in, plug these into the original function. And so we're trying to get it to be the case that negative 2x plus 5 minus negative 2c plus 5 in absolute values is less than epsilon. We could simplify that a little bit. This is negative 2x plus 5 and then minus 5 with that negative being carried through, and then negative 2c, so that's plus 2c being less than epsilon. So we're trying to show that negative 2x plus 2c is less than epsilon. What could we do? We could bring the 2 outside of these absolute values, and then we'd have negative x plus c. That's the same as 2 times c minus x, or because it's in absolute values, we could have done it in either direction. So I see that this right here is an equal sign, and that equal sign means it's also an if and only if. So I'm wanting this to be less than epsilon. If this is less than 2 times epsilon over 2, then I would have that it's less than epsilon. That would be great. So I can require that c minus x is less than epsilon over 2, and that would do this for me. So basically, all of this is sort of our scratch work before we write our short little proof to show that, yes, this function is continuous. So now we can say, let epsilon be greater than 0. We've found the delta that depends on epsilon that makes this work. We are going to then say, we're going to let delta be epsilon over 2. And so suppose that x minus c, the distance between x and c, is less than epsilon over 2. Then that means that the distance between f of x and f of c is equal to f of x, negative 2x plus 5, minus f of c, negative 2c plus 5, which is equal to negative 2x plus 2c, which is equal to 2 times x minus c, which is then less than 2 times epsilon over 2, which is equal to epsilon. So I have shown that when it's the case that x minus c is less than epsilon over 2, then it's the case that f of x minus f of c is less than epsilon, and therefore f of x is continuous. Now let's define continuity in a metric space. So everything we did above was talking about continuity for a function mapping the real numbers with the usual metric to the real numbers with the usual metric. Now let's just think about it for any metric space. So we have really the same epsilon-delta definition of continuity as above. The only difference is that we're keeping in mind that these distances are of a more general form, just whatever metrics they happen to be. And it might be the case that the sets have different metrics from each other. So here's our definition. Let's let xd and yd prime be metric spaces, and let f be a function mapping x to y. Then f is continuous at the point A in x if, for all epsilon greater than 0, there is a delta greater than 0, such that the distance between x and A being less than delta means that the distance in y between f of x and f of A must be less than epsilon for all x in x. And again, notice that d is the distance in xd in that metric space, and d prime is the distance in y d prime. So these may or may not be the same metrics. And as before, if a function is continuous for each x in x, for all points in x, then we say the function is continuous overall. Let's also just note that for functions f mapping the real numbers to the real numbers with the usual metric, this definition is exactly the same as the one we had above for continuity. The usual metric in the real numbers is the distance between x and y is just the absolute value of x minus y. So if you just plug that into this definition, then that's exactly our epsilon delta definition of continuity for real numbers with the usual metric. So let's now look at a couple examples. So I'd like you to think about whether the following functions are continuous. So first of all, just determine whether or not you think they are, and then in either case, either prove that the functions are continuous or prove that they are not using this definition of continuity. So here are our examples. First of all, let d prime be the max metric and t be the taxicab metric. Just as a reminder over here, the max metric between 2 points is the maximum of the distances between their coordinates. And the taxicab metric, that's like, you're driving up blocks in Manhattan or whatever. So it's the sum of the distances in the coordinates. So let's define f mapping the real numbers cross the real numbers with the max metric to the real numbers cross the real numbers with the taxicab metric by f of ab is ab. So in other words, this is basically just the identity function. 1, 4 goes to 1, 4. It's just that they're in different metric spaces. So is this a continuous function? 2. So for the next couple, we're going to use the usual metric d or the discrete metric capital D. First of all is the function q mapping the real numbers with the usual metric to the real numbers with the discrete metric. again, just by the identity function this time, by q of x equals x, is that a continuous function? And second, now let's look at h, mapping the real numbers with the usual metric to the real numbers with the usual metric by h of x equals the floor of x. Is that a continuous function? Again, just if you haven't seen it before or as a refresher, this floor function, it just takes any number down to the next integer below it. So it maps 12 to 12. If something's already an integer, it just stays there. It would map 2.7 to 2, next integer below it, at or above it. It would map negative 3.8 to negative 4 and negative 3.1 to negative 4. So maps integers to themselves and maps any real number to the next integer that is below it. So that's the floor function. So is the floor function continuous when h maps the real numbers in the usual metric to the real numbers with the usual metric? And lastly, is g continuous where g is the same function except now we're mapping the real numbers with the discrete metric to the real numbers with the usual metric? So it's a lot of ones to try out, but think about those. We'll go through them in order, and we'll talk about them in a moment. All right, let's look at this function mapping r cross r with the max metric to r cross r with the taxicab metric by just the identity function. So what we're saying is we're going to let epsilon be greater than 0. Is there some delta greater than 0 such that the distance between the 2 points a, b, and xy in the max metric being less than delta implies that the distance between those 2 points in the taxicab metric must be less than epsilon. So does such a delta exist? So let's just think about what each of these metrics are. So the first one, the max metric, that's the maximum of the distances between the coordinates. So is there such a thing such that that being less than some delta implies that the sum of the distances of the coordinates, x minus a in absolute value plus y minus b in absolute value, is less than epsilon? Well, for that to be true, that would mean that, these two together have to be less than epsilon. That would work if this is less than epsilon over 2 and that one is also less than epsilon over 2. When would that be true? Well, if the maximum of these was less than epsilon over 2, that happens to be the same as before, that's just a coincidence. If the maximum of those is less than epsilon over 2, then yes, each of them would be less than epsilon over 2, making the distance in the taxicab metric between them less than epsilon over 2. So it seems to be saying yes. So let's write that out. Let epsilon be greater than 0. Let delta equal epsilon over 2. And so that tells us that if the distance between a and b and x and y is less than epsilon over 2, then that tells us that both a minus, or both x minus a is less than epsilon over 2, and y minus b is less than epsilon over 2. And that tells us then that x minus a plus y minus b is less than epsilon over 2 plus epsilon over 2, which is epsilon. And so, great, I've done what I needed to do. I have, for any epsilon greater than 0, found a delta that makes this work, and so f is continuous. Let's look at our next example. Here we've got the identity function given by q of x equals x, mapping the real numbers with the usual metric to the real numbers with the discrete metric. Over here, just a quick reminder of the discrete metric. Distance between x and y is 0 if x equals y, 1 if x is not equal to y. So our question of continuity is to say, okay, for any epsilon greater than 0, is it the case that there is some delta greater than 0 such that the distance between x and y being less than delta implies that the distance between q of x and q of y is less than epsilon? Here, the distance between q of x and q of y, that's just the distance between x and y because, again, this is the identity function. So is there such, for any epsilon greater than 0, is there such a delta? Here our answer is going to be no, because if we pick some epsilon less than 1, so if we have 0 less than epsilon, which is less than 1, let's say we have epsilon equals a fourth. So if epsilon equals a fourth, then we know that nothing aside from x is of distance less than a fourth from x, right? So to show formally that this function is not continuous, using our definition of continuity, we could say let epsilon be a fourth, and let delta be greater than 0. So we want to show there is no delta such that this statement above works. Then consider x minus x plus delta over 2. Now these are 2 points who have distance less than delta from one another in the real numbers with the usual metric. Then this is less than delta, but it's the case that the distance between x and x plus delta over 2 in the discrete metric is equal to 1, which is greater than epsilon equals 1/4. So I've chosen an epsilon greater than 0 such that there is no delta greater than 0 that makes this work. In other words, there exists epsilon greater than 0 such that for any delta greater than 0, x minus y less than delta does not necessarily imply that the distance between x and y in the discrete metric is less than epsilon. Therefore, this function is not continuous. Therefore, q of x is not continuous. And in fact, we didn't just show that this function is discontinuous or not continuous because it isn't continuous at some specific point. We showed it's not continuous for any real number x. So in other words, this is discontinuous at all x in the real numbers. Okay, let's look at our next example. We've got h mapping the real numbers with the usual metric to the real numbers with the usual metric by h of x equals the floor of x, the floor function. So visually, this is what our function is going to look like. And again, we can see just immediately looking at it, like we're going to have to lift our pencil. We're going to have to lift our pencil when we draw this function at any integer, right? So this function is going to be discontinuous for any integer, and therefore is not a continuous function overall. So let's prove this using our definition. Again, we could pick, what is this jump that we're making? We're making a jump of 1. So we could let epsilon be any number that is greater than 0 but less than 1. Let's let epsilon be a third this time. And so, where are our issues going to occur? Our issues are going to occur at integers. So let's say, let's consider x equals 3. So consider x equals 3, and let's let delta be some number that's greater than 0. Then if we look at, where does the issue occur? The issue occurs at being right at 3 versus being a little bit less than 3, right? So we could look at the distance in the usual metric between 3 and 3 minus delta over 2. So if we look at the distance between 3 and 3 minus delta over 2, then that would be equal to 3 minus delta over 2. In absolute values, that's equal to delta over 2, which is less than delta. However, if we look at h of 3 minus h of 3 minus delta over 2, then what have we got? That would be equal to, h of 3 is just 3, but h of 3 minus delta over 2 is 2, because it's over here, it's a little bit less than 3, has an output of 2, and so that distance would be 1 between those values, which is greater than our epsilon, which was 1/3. So this tells us that, therefore, this function h is not continuous because it is not continuous at a specific point. Specifically, it's not continuous at any integer. Not continuous at x equals k for any k in the integers, and therefore the function is not continuous overall. Now let's look at our last example. Here we're looking at the same function, g of x is equal to the floor function, but instead now we're mapping the real numbers with the discrete metric to the real numbers with the usual metric. So could this be continuous? So in other words, we're saying, is it the case for any epsilon greater than 0 that there's some delta greater than 0 such that the distance in the discrete metric between x and y being less than delta implies that the distance between g of x and g of y in the usual metric is less than epsilon? Is that true? Well, let's just think about what it means for the distance between x and y to be less than delta in the discrete metric. Let's say that delta is 1/2, is something less than 1 but greater than 0. Then distance between x and y being less than 1/2, what does that mean? That actually means that x is equal to y because we're in the discrete metric where points are either of distance 0 from one another, in which case they're equal, or 1 from one another if they're not equal. And this would imply that then the distance in the usual metric, g of x minus g of y, would then be the absolute value of g of x floor function x minus g of y floor function, but x equals y, so this is just x again. And so this would be floor function of x minus floor function of x. What is that? That is 0, and it's certainly less than epsilon for any epsilon greater than 0. So we've shown that for any epsilon greater than 0, there is a delta. Delta is 1/2. It does not actually depend on epsilon, such that the distance between x and y being less than 1/2 implies that the distance between g of x and g of y is less than epsilon. So this tells us that this floor function is continuous. This is a funny function. This function, which looks very not continuous, it does depend on the metric spaces we're talking about. So this function right here is continuous if we're talking about mapping the real numbers with a discrete metric to the real numbers with the usual metric.